We get started. All right, everybody. I think we're finally ready. This is our first seminar of the new year, so thank you for everybody for joining us. First order of business, maybe the most important order of business, is to thank all of our sponsors, and we've got a number of them this year, thankfully. Toyota, Mitsubishi, Qualcomm, Seagate, and the MathWorks are all sponsors this year, so that's really great. We appreciate their support. That gives us the cookies and coffee, which is what brings everybody. In addition, thank you. In addition to another great, round of speakers, the first of which for this year is David Friedrich-Kyle, who's a faculty member at UT Austin. I met him while he was a graduate student at Berkeley. We were working, I think, on an O&R project together. So I've seen his work for a long time, so I'm happy to introduce him here. He's an NSF GRFP winner and an NSF Career Award winner, amongst other things. And so doing a lot of great work in multi-agent games and game theory, and he's going to tell us about some of that today. And so without further ado, I'll let you take it away.
Okay, thanks so much, Pete. Okay, and thanks everybody for being here. It's great to start off the control seminar for this season and to tell you about some of the work we've been doing in my group for the past couple of years. I titled the talk Variations on a Theme, Information Structure, Equilibria, and Dynamic Games. It's really like structured as like 1/3, maybe 1/2, like digging into very classical results from linear quadratic problems in games. And I want to like basically dig through these and derive the core results and show some structure that then we'll exploit in some, hopefully interesting and new ways for the rest of the talk. Okay. I actually got into games because I interned at a self-driving car company midway through graduate school. So we were doing trajectory planning for cars. And so that's what the sort of left-hand photo is meant to evoke. But more recently, I've sort of found other applications in games in power systems, and actually with colleague here at Michigan, Max Lee. I don't think he's able to be here with us in person right now, but maybe he's on Zoom, Max, anyway. So we've been studying routing games and hierarchical problems in those spaces. Okay, so I want to just walk through this sort of scenario of trajectory planning in cars, just to show you how I got into this problem and hopefully help everyone here connect to some of the interesting parts. So if you're imagining that you're, let's say, one of these vehicles and you're trying to plan a lane change, the kind of natural thing to do would be to think about this as a trajectory optimization problem and maybe try to do some sort of model predictive control. And what I'll hopefully convince you of is that actually a more natural way to think about this is through like a model predictive sort of game that you solve. So the kind of MPC view of like the trajectory optimization problem for this car would be to write down some objective function that basically specifies what it means to change a lane, enforce dynamic feasibility as a constraint, enforce that you know where you start, maybe enforce collision avoidance constraints or other actuator limits or things like this. And solve this and then repeat in a receding time horizon. So super familiar, hopefully to most everybody. In reality though, there are other cars in this picture. So I've just highlighted a couple of them and illustrated that maybe the objective function or some of the constraints perhaps might depend upon what you think these other drivers are going to do. So here I've just picked out the state trajectories x2 and x3 for agents 2 and 3 and thrown them into the objective function and just used that to illustrate this connection. Okay, so far so good. And now the connection to game theory is just to realize that actually these other agents in the picture are other decision makers. And so where do those state trajectories come from? They come from decisions that are made by those other agents. So in reality, maybe a better model of this interaction is to say that there are 3 coupled optimization problems. Each agent is choosing an optimal control sequence that influences their state trajectory that then influences the other's costs or constraints. So this immediately gives rise to a game. All right, so there are a few key ingredients of a dynamic game, a game that's played over time. So I mentioned objectives. So every player, every agent needs to have some sort of cost. There are states of the game. I'm always going to use superscripts to be player index, subscripts to be time, just for the sake of consistency. There are rules to the game or dynamics, nothing super surprising here. And then the most interesting or subtle part that we'll be focusing on pretty much for the rest of the hour is information structure. So there's a lot of subtlety to information structure and different ways to describe it, but I think the basic colloquial explanation would be information structure is the designation of what information each player knows when they have to make a decision at any given time. Okay, so you think about player I's action at time t as some function of something, and what's the something? That's the information structure. There's also all kinds of different solution concepts in games. In this talk, we'll be looking at two refinements of the Nash equilibrium concept. It's obviously a popular one, but basically the Nash equilibrium is just a point in this space of strategies for all players where no player has a unilateral sort of incentive to change. Okay, but we'll be looking at some refinements of this idea. All right, so with that out of the way, I've structured the talk in these four categories. We'll really start up here and walk through these like very classical building blocks. These are things that when I first got exposed to this this theory as a graduate student, I just assumed had been beat to death, and there was nothing new here. But I think I have learned a ton by walking back through all these classical derivations and sort of seeing what structure arises and how the solution methods and answers change when information patterns change. And that's been very fruitful. So that's going to lead us then to kind of talk through three little vignettes after that. All right. So the building block for the rest of the talk is going to be the linear quadratic game. So it's the kind of multi-agent, non-cooperative variant of LQR. This is the control seminar. I'll assume everybody is very well versed. So this is, like I said, the n-player non-cooperative version of LQR. So there's just n copies here, and the ith player's problem looks like this. So what's player I doing? They're minimizing a quadratic cost structure. That quadratic function up top depends upon the state of the game X. So this is kind of shared among all the players. It's like the state of the board in chess, for example. And it also depends quadratically upon all the other players' actions over time, the U, J, T's, for all players J. There's also linear dynamics down here. So this is the state evolving linearly as a function of all of the players' actions. Okay, so one interesting thing I want to point out, it'll come back later in an interesting way, I hope, is that this term up here throws people for a loop often. So this term here is saying player I incurs some cost as a function of player J's decision at time t. Like, why would you ever have that? That was some question I had at first when I saw this. The example I'll show you later is actually about politeness. So if I'm driving a car and I want to make a lane change, well, I don't really want to do it in a way that forces the guy next to me to like hard brake. So a way to encode that would be to penalize me, player I, for player J's control actuation.
May I ask something?
Yeah.
So here, essentially, if you have the dynamics AT, BT, so intuitively this means that me as a car, I change my state. I know how this is going to affect the other car state, assuming that they know their control inputs.
Yeah. So maybe building on that, a really natural thing you'd see in multi-agent systems would be for the state of the game to kind of be like a concatenation of individual vehicles' states. So if there's three cars, maybe each one of them has some individual states, and X here is just like player one's variables, player two variables, player three variables stacked up. Yeah. Okay. So this leads us to talk about information. There's two like extremes in the space of information patterns. One is feedback patterns, the other is open loop patterns. So I think the naming is a little unfortunate because a feedback pattern, of course, is where you assume in state feedback, the state at every time. So it's like saying, you have your eyes open when you play the game. You get to look at the board when you make the move in chess. Open loop patterns, it's like, you have your eyes closed when you make the move. So, you know what time it is, it's your move, but anyway, and the initial condition, but you don't know the current state. So that's open loop strategies. Eyes open, eyes closed. Okay, so let me try to keep this interactive. And this example I'll show you in a minute the point is to try to illustrate why these two information patterns are really truly different, why they lead to different solutions in these basic linear quadratic setting. So, okay, so this is a linear quadratic game. Actually, well, okay, let me avoid that subtlety. So it's a linear quadratic game. The dynamics pretend they're point masses. So like double integrators, there's maybe some initial velocity vector, but actions are accelerations. Player one wants player two to go to the origin, so some quadratic description of that. Player two wants to get close to player one. Again, just subtract the state's quadratic cost. Both want small controls, so quadratic penalty on control. It's a linear quadratic game. Turns out the way I set it up, it's there's unique solutions in a finite horizon variant version of this problem. And I've shown both of them. I've shown the open loop solution and the feedback solution in different colors. In this case, player one's starting down here, player two's starting up there. Take a second and just think through which do you think is which. So as you're thinking, I'll repeat the setting. Player one wants player two to go towards the origin. Player two wants to go towards player one. Neither wants to exert much control effort. Double integrator dynamics. The initial velocity vector for player one is pointed that way. The initial velocity vector for player two is sort of pointed down. Which is which? Feedback pattern would be where you get to see the state at each time. And the state here is both agents' states.
And the green one is the closed loop since it seems to behave better.
Yes, yeah. Green is feedback, okay, and blue is open loop. And thank you. Yeah. So okay. So basically, why is feedback the solution in green? What you should think about is player one knows that player two is going to see it over time. Okay. So player knows that any moment in time, player two will see where player one is. Player two wants to go towards player one. So the right thing for player two to do is to go towards the origin. It kind of give player two a reason to go that way. And anyway, that's the solution. In blue is open loop. And what's going on here is more subtle. So player one knows that there's an open loop information pattern. So player one knows no matter what he does, player two is never going to see him ever again. So there's nothing player one chooses to do will have any influence on what player two should decide to do. Okay, so player one is lazy and wants to exert low control effort, so the right thing to do is do nothing. Okay, so he had an initial velocity vector pointed this way, so he's just going to keep going. Now, this is a Nash equilibrium we're describing, so we want to think of a point in strategy space where both players, neither one has a unilateral, incentive to change. So if player one is just going to head this way, the kind of best response to that is for player two to kind of start to approach. Okay, and that's the explanation. Okay, so these are clearly different answers. I told you it's a linear quadratic problem. You can just trust me. In this case, there's a unique solution for both cases. So there's no magic going on. There's no subtlety. I mean, I'm not hiding anything. This is a unique answer. Okay. So I think one lesson that I drew from this when I first saw this example from a friend was that actually kind of closing the loop in receding horizon is really dangerous here. So it's something that's really natural for anybody thinking about this from a model predictive control sort of single agent decision-making standpoint. You think about solving LQR and you derive the feedback loop from the Riccati equation and you just rock and roll. That'll basically give you the same answer as just solving the QP that's LQR in a receding time horizon. I mean, without disturbances or anything. So receding horizon sort of closed loop, setups make a lot of sense in single agent context, and they immediately break here. If you just solve the open loop problem in a receding time horizon, you're never going to go to the origin. So the behavior is totally different. I don't care how fast you do it.
Excuse me.
Yeah.
Is this because you have finite horizon in the receding horizon, or
no? It is. So we'll see the reason. Yeah. Okay. So let's dig in, and I promised we would sort of derive these things and see structure. So let's kind of go ahead and do that. we'll start with the open loop setting. I think it's a little bit easier to talk through. So open loop strategies and discrete time, it's just a time indexed sequence of actions, right? So the way you get there is we're in a linear quadratic setting. So assuming some convexity, all you need to do is write down the KKT conditions for the ith player and solve them. So I've just started by writing down the ith player's Lagrangian. I've introduced multipliers or co-states for the kind of dynamic feasibility constraints, and that's what we've got. Okay. As soon as you do this, you can write down KKT conditions. Here, there's no inequality constraints. It's sort of the most basic version of linear quadratic decision problem. So no complementarity showing up or anything. And you can, we don't need to stare at this too hard, but there's some equations. Okay. And the kind of important thing to realize is that this is just a linear system of equations in the variables state X, control U for all players, and Lagrange multipliers. Okay. These are just linear equations. It's also very sparse and very highly structured, so it's probably no surprise to most of us here that there's a recursive Riccati type solution. So again, I don't want anybody to stare at this too hard. There's not much point yet, but after a little bit of work, you can get a recursive solution. Okay. I highlighted some matrices just because actually this one here is going to come back later. Yeah.
You're calling this the open loop solution, but the way you've written it on the left side, maybe I'm misunderstanding, like the UTI looks like it's in a feedback form.
That's an excellent point. So it does look that way, but this is actually only valid at the equilibrium trajectory. Yeah. Yeah. But it's,
I would think like when I do the one agent LQR problem, I do the same type of solution, and then I just argue like, oh, I could implement this in the state feedback. So, is that an incorrect way?
No. So what happens is you can totally do that in the one agent LQR setting, but what'll happen is that matrix sitting in front of X is going to be the same matrix you'd get from doing the dynamic programming solution. Okay. What's going to happen in just a hot second is you'll see it's different. Okay. Yeah. Which is why those answers deviated before. Okay. So in the feedback case, there's a very important refinement to the equilibrium concept. So feedback, I forget exactly who this conversation was with earlier today, but feedback has a meaning that's so it has a meaning that's to say you see the state, that it has a meaning regarding information, but it also has a meaning regarding optimality. So if you think about the Bellman principle of optimality, turns out that in game theory, when people describe feedback Nash equilibria or feedback Stackelberg equilibria, the term feedback there means that you are enforcing this sort of like strong time consistency, dynamic programming type argument. So the point is a set of feedback Nash equilibrium strategies must be in equilibrium sort of no matter the state you're at and no matter the time you're at for the rest of time. So it's saying that, if I find myself in whatever state at whatever time, I'm happy continuing to play these strategies, or all the players are happy. Put another way, okay, think about it this way. Every open loop strategy can be realized with the feedback strategy. I just ignore the state and play whatever you told me to play in open. Okay, so therefore, every open loop Nash equilibrium pair of strategies is Nash equilibrium in the space of feedback strategies. It's just a stupid one, but it is one. So when you say feedback Nash equilibrium, it's sort of useless to talk about Nash equilibrium in the space of feedback strategies. You have to add this extra kind of principle of optimality type refinements. And so that's what gives rise to the dynamic programming solutions that are very classical. So, this is going to be super familiar, just the standard type derivation of LQR, and I'm just going to slap superscripts for different players on here, but the derivation is the same. What you do is you construct a sort of cost to go function for each player, function of the state and the time. And so that's what you do. Start at the end of time, assume there's nothing, the world ends after this time, so there's no cost to go after this. Solve for the equilibrium, so whatever state X capital T the game ends at, what's the equilibrium controls all the players should apply at that time, assuming, I think it's going to say, assuming some convexity of these cost functions. The right thing to do is to do nothing. And basically the standard thing that happens in LQR is you realize that as the recursion goes backward in time, we'll see one more step. The optimal cost to go has a quadratic structure. So probably very familiar. As you move backward one step in time, this is the expression for the cost to go for the ith player. And you write down the first order necessary conditions. It's a convex problem. This is for the ith player. So we just got to do this for all n players. If you do that, you get somewhere like this. And it's again, just a big system of equations. So there's some matrix that hits the equilibrium controls for all the players. And you've got to solve it against this vector. Okay. All right, so again, let's not stare at this too hard yet. But one interesting thing that happens is you can be a little clever and realize, okay, this guy over here, the state was showing up. So that can be factored out. And you can solve a different, basically same system of equations for the sort of feedback gains that hit the state for each player at equilibrium. And that's where that feedback matrix comes from, but it's a different one. It's one that solves this system of equations. Okay. And then at the end of the day, you of course have to plug this back into the cost to go and sort of rederive the recursion. And we don't need to stare at this too hard yet. Okay, so what changed? We saw two slightly gory systems of equations. One thing that takes a little bit of time to stare at this and figure out is that in this recursion that I just ended the last slide with for the cost to go for the ith player, there's a term here. This is the one I pointed out before. It's the kind of determining how much cost player I incurs for player J's action. Well, it's showing up. You can trust me, but it wasn't showing up in the open loop solution. In those recursions we derived in the open loop setting, that matrix was not there. So even though it was there in the original cost structure for the problem, it disappeared in the solution. Okay, let me show you why. So let's say that I want to be polite. I want to care about somebody else's control effort. There's maybe structure like this. So maybe I'm player one. I have some nominal cost J tilde, and I want to augment it by adding some, norm, let's say, of the other guy's control action. Okay. Well, that's fine. But in open loop, what's going to happen is I'm going to write down the Lagrangian for myself, and I'm going to take a derivative with respect to my primal variables, my controls and state. And as soon as I do that, I realize, well, this is the other guy's decision variable, not mine. So if I differentiate with respect to state or my controls, this thing goes away. So it's as though it wasn't there. It doesn't even affect my optimal decision. Slightly weird. But what happens in feedback is that actually it doesn't go away, because you realize that there's this added constraint that says, okay, in the future, player two's decision depends upon the state in the future, which depends upon my action now. And since I can, influence the state in the future, I can influence the other guy's action in the future. And so, some of these derivatives don't die. And so that's why the feedback solution includes that term. All right. So hopefully we've set the stage a little bit. I want to pick out a couple different subtleties of these systems of equations and show hopefully something interesting we can do with them. So the first question I'll kind of ask is, how can we find approximate feedback Nash equilibrium strategies which kind of minimize some notion of interagent communication or sensing? So why do we even care about this? I was visiting JPL last summer, and I happened to speak with a fellow who was one of the tech leads for this Cadre mission. Cadre is a tech demo that NASA is running. They're launching 3 rovers up to the moon. they're equipped with like a ground penetrating radar sensor, and they have to keep close formation in order to basically get good sensor readings. So at least as he explained to me, one of the major design issues that they were designing around was that they wanted to minimize the communication between the agents because that cost limited power. Anyway, so right. All right, so where does all of this come into play? Go think back to the system of equations that defined the feedback Nash equilibrium strategies. This was what it looks like. There was some enormous matrix S, the feedback strategies for all the players, and something over here. Okay. And back to your comment earlier, in this type of setting, it's really natural for the state of the game to be comprised of to have a block structure. So like the state of rover 1, the state of rover 2, state of rover 3, all stacked up in a big vector. So that block structure for the state induces a block structure on these feedback gains. Okay, so what's happening is like the ith player's feedback matrix at time t has like blocks of columns. Each one hits a different block of rows of the state vector. Okay, and so if I want to minimize player i's dependence upon other agents, you can think of it as maybe zeroing out blocks of this matrix. Okay, and that leads us immediately to like a little idea here, which is why don't we just solve that system of equations, but like regularize it a bit and regularize the like group L1 norm. So basically solve a problem like this. Okay, so like take each of these blocks, penalize its Frobenius norm, and otherwise just use that to regularize the original problem. This turns out to be like a nice convex problem you can solve. It's super well studied. It's just like not hard to solve this at all. And the other kind of nice, I guess, property here is, remember, this linear system of equations was part of a dynamic program. So it was like standard LQR style derivation. You're working backwards in time. Each time you're, in this case, solving a big system of equations to get these feedback gains. All we're doing is changing how you get the feedback gains, but then there's another step to the dynamic program and so on. So the upshot is, you're kind of baking in the knowledge of sparsity as you work backwards in time. And that has interesting effects. So here's, we'll kind of see a couple examples. This is actually not formation keeping. This is like a collision avoidance problem. But anyway, I'm showing a case where there's 4 little rovers. They each have an initial position and a goal. They each have some cost function. And I'm showing the kind of original feedback Nash solution over here at just some moment in time. And you can see it's pretty dense. Over here is the one where we've regularized. And you see there's a lot more block sparsity. And I just picked out some random moment in time. And you can see kind of like over time, as I play a video, the sparsity patterns really change. I can even just play it again real quick. Okay. So like, just to quickly zoom in on what's happening, what I'm plotting here is each of these 4 subplots is tracking the number of other agents that the ith player cares about for player 1, 2, 3, and 4. So I'm plotting that for different levels of regularization, and sort of the intuitive thing you'd expect is that as I penalize sort of inter-agent dependencies more, as lambda gets bigger here, you should see these things get smaller, and basically each agent should care about fewer others. But there are some interesting sorts of counterintuitive effects that arise because of the dynamic programming. So for example, here, when I don't regularize at time, like time index, whatever this is, 60 something, I only care about 3 other players. Totally unregularized problem. But when I do regularize a healthy amount in the red, I actually decide it's important for me to like look at this 4th agent. And the reason it's important is so that I can be way sparser later, so that I can ignore them for way more time later. So this all gets sort of baked into the dynamic programming procedure, which is sort of something you get for free. Okay. So that's vignette number one. Let me change gears and show you something totally different, still related to linear quadratic problems. But let's imagine a scenario where your access to information changes during the scenario. And it switches between open loop and feedback structure. I'll show you an example of why this might happen in a minute, but is it possible to find an equilibrium efficiently? So here's the scenario that kind of led me to this type of problem. So, I'm overtaking somebody on the highway, and if I'm stuck behind the big truck, I can't see the oncoming traffic. So if there was a car there, we'd sort of be playing an open loop problem. But as soon as I poke my head out, we see each other, so we're playing feedback. And then if he's too close to me, I have to, go back behind the truck, and we're playing open loop again. So you can imagine that this could interleave. Anyway, just one example. So in linear quadratic problems, what happens is, we saw that basically both the open loop and the feedback Riccati solutions encode, there's some sort of feedback-esque term that Pete recognized in the open loop case, and that definitely is like familiar in the feedback case. And these actually relate to some concept of cost to go. And the difference is that in the feedback derivation, the cost to go is kind of a global measure of cost to go. It's sort of state independent. You plug in the state, I tell you the cost to go. In open loop, what's happening, I think it's going to show up here. In open loop, what's happening is actually like all of this is only relevant along the equilibrium trajectory. So basically this, this guy here, you can see he's accumulating sort of state cost matrices and some other nonsense. This is actually only a kind of a local measure of cost to go around the equilibrium trajectory. So the analog here is basically like this M that we got from solving KKT conditions in the open loop problem, sort of playing a similar role as this Z here that was defining the feedback cost to go. Okay, so with that little observation, blah, 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 it's not too much of a stretch to think about, okay, if we have different kind of intervals of time in which we're playing like open loop and feedback and open loop and feedback over different intervals of time during an interaction, what you could do is kind of like, okay, start at the end of time, work your way backwards, solve an open loop problem. Take the M matrix that I showed on the previous slide, plug it in as the terminal cost for the feedback part, continue the DP, then solve another open loop problem with that as the terminal cost and continue. And there's caveats here. So you have to be careful about like where these things link up. The open loop problem, remember, is like everything is, the strategy assumes the initial condition. So you sort of have to parameterize the solution to this problem on the initial condition at this time and kind of stitch everything together carefully. But at the end of the day, this ends up, again, just being a linear system of equations to solve. So it's super efficient. So the last thing I want to leave you with is that despite the fact that, I think there's been a very deep understanding of these linear quadratic game problems for many, many decades now, there are still interesting theoretical results to be had that relate to them. So let me just kind of show you some of our recent, recent esoteric, but I think useful directions that we've been going here. So the first thing to say is that actually everything we've talked about so far, and the reason I've focused so much on linear quadratic problems is because there's very easy extensions of a lot of the ideas beyond that setting. So the point to make here is that if you think about the difference between an LQR problem and some non-convex trajectory optimization problem, what's the relationship? So if I take a non-convex trajectory optimization problem for one, single vehicle, and I write down the first order optimality conditions, and then I take a Newton step on those conditions. The Newton direction I'll be computing is very, very similar to the LQR solution you would compute. Okay, for like a linearized system and a quadratic approximation to the cost at that point. So there's this deep connection that's been known since the 60s, really, for relating non-convex optimization and LQR. And so that's basically why I study all these things in the linear quadratic setting, because there's this very natural recipe for relating linear quadratic solutions to more general problems. Okay. So, all right. So we're starting to talk about non-convex problems here. So in non-convex settings, open loop solutions are way simpler to compute. How do you do that? Sort of like I just said, what you do is you look at players' first order optimality conditions. It's a big system of equations. Maybe it's a complementarity program because you have inequality constraints or something. Solve it. Get a first order, KKT point, and go and check second order conditions, and cross your fingers. So like that's not that hard to do. There's solvers for this. The price you pay for that, obviously in a non-convex setting, you're not hoping for anything global. You're just getting some sort of local concept of equilibrium. So you're paying that. The real price you pay, in my opinion, is that you're forcing an open loop information pattern here. So you're basically forcing players to kind of commit to sequences of actions independent of what the state is doing. So that's a huge price you pay. On the feedback side, what's happening is, of course, you have a bigger strategy space, so you're encoding more complicated behavior. But the price you pay is that it's way harder to compute. And actually, the state-of-the-art solvers here, unless there's a lot of structure, is basically they can only even approximate the first order conditions at a solution point. So there's really like a lot of caveats to what state-of-the-art solvers can do in these problems. So this led us. So I was the context for all of this is I was talking with a contact at Lincoln Lab who was working on a satellite, kind of adversarial satellite rendezvous type problem. And so he came and he's thinking, hey, this is a zero-sum problem. Its simplest case would be finite time horizon. Definitely non-convex. There's all kinds of collision avoidance sorts of constraints that make it non-convex. There are actuator limits, of course. So I can only exert so much thrust. I need to run it fast online. Can you build me a solver for this? So what I told him was, I think I can. And I definitely can start with the open loop solver because I sort of know the recipe. So we started with that. And then I kind of always had in the back of my head that this thought that probably, certainly we would have to go and build a feedback solver after. And then a friend of mine basically sent me a screenshot from Tamer Bashar's textbook, which if you haven't read, it's a very nice reference. It's a good book. Anyway, I was embarrassed that I hadn't seen this before. What basically the screenshot was some proposition that said under some conditions, in zero-sum problems, LQ problems, open loop and feedback solutions give the same exact answer, same exact trajectory. Okay, didn't know that. That was something I had yet to learn, and so I was wondering, okay, well, we're solving a non-convex problem. It's definitely not linear quadratic. Like, did this result basically just like save our free lunch? Like, can we? Yeah.
Just to go to the example you gave earlier, where one is trying to drive two to the origin, and
that's a general sum problem.
so
yeah.
Those what they're optimizing is different things. So
yes.
Zero sum in that case, they'd have to be like negatives of each.
Yes. Yeah. So sorry, in a zero sum problem, it's the objectives add to zero. Yeah. Yeah. So those are like purely adversarial. There's absolutely nothing aligned about players' objectives. Yeah. Okay. So why bother with feedback solutions anyway? Yeah. So right in this general sum example we saw, we've definitely seen that open loop and feedback solutions can differ substantially. But in this zero sum context, the question was like, hey, maybe there's this existing result that's pointing that maybe they're the same answer. So if I already have a solver that I built for the zero sum case that's pretty good, has some nice convergence properties, blah blah blah, do I need to bother spend a year or two working on the feedback problem? Do I already have the right answer? Okay. And so let me walk through the classical results that we ended up digging out after we got this screenshot. Okay, so we're not going to dwell on these too hard, but basically in convex concave zero sum linear quadratic problems, there's and uniqueness assumptions, some like a feedback solution is also an open loop solution. This is a similar statement, but basically relaxing the convexity concavity assumption, blah, blah, blah. And yeah, so, and then when they both exist, kind of unique open loop and feedback solutions coincide. So this is all linear quadratic. There are some results also beyond the linear quadratic setting. And I'll kind of blow through these quickly, but the basic restriction here is problematic. The basic restriction is this assumption of uniqueness, and it's actually a worse than uniqueness. It's this thing called strong uniqueness. Strong uniqueness is so it's saying we're at a unique equilibrium point, so there's only one of them, and more than that, if player I looks out at the other, well, I guess two players zero sum here. So player one looks at player two, says, okay, I know your strategy. I have a unique best response to you, and vice versa. So like, why is this a little subtle? Think about rock, paper, scissors. Rock, paper, scissors, simple game. Everybody knows there's only one kind of equilibrium strategy, which is to play, 1/3, 1/3, 1/3 on rock, paper, scissors. But, if Dan says, hey, my strategy is 1/3, 1/3, 1/3, David, what are you going to do? Turns out, I don't care. I can play anything I want, and the expected outcome of the game is, even odds of winning and losing. So I don't have a unique best response. So therefore, that unique equilibrium of 1/3, 1/3, 1/3 is not strong. Okay. So anyway, the point is, these results that exist in the literature are nice, but they have this enormous caveat, which is particularly bad in non-convex settings where I don't even know about uniqueness, let alone strong uniqueness. I can't even find a solution. All I can hope to find is a local solution. So like, this is useless to me. Okay. So, all right. So this leads us to talk about local solutions a little bit. So local solutions, just like in optimization, you would talk about first order, gradients of Lagrangian equals 0, et cetera, conditions, and second order conditions that relate the kind of Hessian positive definiteness on critical cones. So those are the types of necessary and sufficient conditions for local optimality in optimization problems. You have the same types of conditions show up in games. In games, it's basically just you take the gradient of player I's Lagrangian with respect to its decision variables should be 0 and constraints should be satisfied and complementarity and blah, blah, blah. Second order sufficient condition, again, should basically be, okay, these things are holding, and also the Hessian of the ith player's Lagrangian should be positive definite when restricted to its critical cone. So, this is the basic idea. Okay, so we then basically tried to see what results could we replicate from the LQ or even non-LQ settings in this local case. And so we were able to basically prove some very analogous results, but the techniques are very different. So the summary of all of this is basically to say that under some marginal assumptions, feedback and open loop local solutions coincide. And what's interesting, I don't have a slide about it, but just to kind of give you some sense of the proof technique, the way this all works is, remember, what is the feedback solution? A feedback solution is what you're doing is you're saying, I need to enforce that in the future, at whatever state, the equilibrium trajectory follows, the other guy is going to follow an equilibrium policy, which is to say they're going to solve some equilibrium problem that is conditioned on that state, parameterized by that state, and going into the future. So there's this sort of nesting that happens. that's a constraint. So you're literally constraining the choice of future control decisions by other players in the future. It's a constraint, so it needs a Lagrange multiplier. So the like proof technique essentially relies upon showing algebraically that Lagrange multiplier is 0. And if that Lagrange multiplier is 0, the constraint's not active, and it basically doesn't influence anything. So that's how we basically show these things. Okay. That's like all I prepared. I want to leave you with a couple thoughts. So dynamic games are very flexible. Information structure is like super interesting and really underexplored. And even though these things have been like kind of beat to death, there are still some cool results to be had. So that's kind of all I brought. I want to thank everybody here, open it for questions, and also thank all of my students. Yeah.
I think we have time for some questions if people have them. Go ahead, Jim.
Very nice talk. I'm curious, so, you compare the open, said, with open loop, R doesn't show up anywhere in C,
Yeah.
right?
Yeah.
So that got me thinking, is there something special that would happen if you constrain your problem data so that R is block diagonal and each block being separate? Layer? So in other words, all the RIJs are 0 except
Yeah.
for the RI.
Yeah.
Is there something special about that particular case? I have a reason for asking that.
Okay.
The reason is, could you not just overbound the full matrix R by a block diagonal and get a conservative solution?
Oh, I see what you're asking. I think the short answer is, without doing a lot of algebra, I don't know the answer. But my hunch is that there are other things going on, and that wouldn't get. So there is a recent paper that came from a colleague, Nagar Mir, if you've seen any of her work. But basically, I think what they did is they basically tried to bound the difference in equilibrium trajectories between open loop and feedback solutions. I don't know if there was a restriction to LQ problems, but I bet there was. And I think what they did, kind of related to your idea, I think they basically tried to bound the difference in terms of the kind of off diagonal blocks of this R block matrix. Yeah.
Questions?
Piggyback on that, just maybe ask one quick question. A lot of the examples that you gave, the dynamics are decoupled, agents moving around. I mean, unless you had like wind effects or something.
Yeah,
like that,
sure.
But they're coupled through the R matrix.
Yeah.
So what if the cost is decoupled, which is kind of, I think, what Jeff was getting at, but the
Oh, sure.
dynamics are coupled.
Oh, well, so I think first, like the Q can still couple stuff, right? So you can still have coupled state costs.
Yeah.
Sorry, but if the dynamics are coupled, yeah, so then I mean, yeah, that's going to show up, right? So like when you so here, well, I guess I should put it up here. So right, like if A is coupled stuff, that's going to show up.
Is there anything that you can exploit of the dynamics? Like in all the examples you gave, the A would be block diagonal if the dynamics were decoupled. Does that lead to anything special? It's really only the cost that's coupling things.
Yeah, I mean, maybe computationally speaking, you could exploit some sparse, you could represent maybe like some of this with sparse matrices, but like in any, I think, really interesting problem, you'd have at least Q being sort of dense. So I don't think you can get too much benefit from that. Yeah.
Well, I was wondering, does any of these result also apply to discrete domain?
It's a great question. So actually, there's a story there. The short answer to your question is God only knows. But so the first time I taught my graduate class on game theory, there was a student in the class who was looking for a class project, and I basically suggested a version of that question. I was like, hey, take a game like tic-tac-toe. Obviously, just very discrete, whatever. Is there a way you can find to embed tic-tac-toe as an LQ game? Like, is there some way you can like find some, I don't know, one hot encoding of the state or whatever in which the dynamics are linear and the cost is quadratic to both players. And then, the upshot would be you could just solve it immediately and be done. And so several weeks go by and I come to office hours and this guy knocks. He's like, hey, I'm like really sorry to ask you this, but I'm really afraid for my class projects. Like, I've been trying everything I can think of. Nothing's working. But, I did prove that this is impossible. At least for some construction of the embedding. It's like, why don't you publish this? This is very interesting. It's still unpublished. I don't know. But yeah. So I think it's an open problem.
People have their class project semester that.
Yeah. I can give you the guy's name. You can egg him on. But anyway.
Any other questions?
High level again from me, because I'm not that familiar with linear quadratic games. Apart from formation control, what other context, and what other applications do they find, right?
Yeah, so I think the serious answer I would have to that question is like, I actually don't care about purely linear quadratic problems from an application perspective. The reason I care about them is because I care about nonlinear, non-quadratic problems and finding Newton steps on the KKT conditions for those problems, which end up requiring me to solve linear quadratic problems. So in that setting, where do these linear quadratic problems come from? Well, they come from linearizing the dynamics about some trajectory, taking quadratic, Taylor approximations to players' costs, et cetera.
And maybe I'm trying to understand more, when it is possible for me to connect through a dynamical system, linear or non-linear, my behavior to your behavior.
I'm not sure I understand.
So when we assume, for example, the linear system, or
Yeah.
the whole network operates somehow, right? So essentially, my state somehow affects yours,
Yes.
and I know that somehow.
Oh,
I know that model. So this
yeah.
way, I said, for example, formation control, I can see this
Okay.
arises naturally because we need to keep a formation. Then
You're thinking like what other costs
power
couple the
networks,
decisions of agents?
It's an application just out of curiosity. Power
Sure.
networks, another case, I suspect now that I remember suddenly from some works. Yeah.
Yeah, I mean, I can start giving applications, but basically any setting where like my performance depends upon your decision. So, like a classic example, I reviewed a paper recently was about supply chain modeling.
Yeah.
So in a supply chain, like a standard thing to do would be to model like the decision of one firm as sort of like setting.
Yeah.
Anyway.
Yeah, no, I guess,
Yeah.
it's similar. Yeah, essentially what I was looking, but
Yeah.
it totally makes sense because again, this is like connected to like a power network system where essentially,
Yeah.
if I produce more, you get it more. So
Yeah.
all of this is a network system.
Yeah, I mean, even back to the first example I gave of like the cars planning trajectories on the highway, that's, I mean, basically if I start to execute a lane change, I'm getting close to you. So, you better slow down. Otherwise you're going to get uncomfortable because we're too close. Like that's another setting.
Yeah, thank you. Yeah. It was just a high level question. Yeah,
Sure.
relevant to the tools per se. Yeah.
Maybe we should wrap up. We may get kicked out of this room. I'm not sure if we even have the room past 4:30, but I want to make sure we thank the speaker and then you can come down and ask questions if that's okay.
Yeah. Hopefully we have like lots.
Okay, well, we'll see.
So we'll.
Very good to meet you.
Likewise.
I'm gonna run upstairs, so I'll meet you in the room on the third floor if you're there. Otherwise, I'll see you at actually, I can just meet you at the graduate. So
Okay, well, I think I'll be up there. We'll see. Yeah.
sorry to cut you.
Yeah. Hey, yeah. Hey, thank you. Yeah. All right.
They have brought the coins and they,
Yeah.
I think, open loop might be brought, and in practice.
I don't think it works like super hard in the last few years, but like now I'm on a thing to get everything that. I can credit if I don't really buy it or enough, but then I feel like, oh, I left some stuff in my hand, once.
Yeah, oh yeah, totally.
Yeah, and in practice, it's always noise.
Yeah.
Today it was pretty bad, just staring at random stuff, feeling like I'm saying this. Yeah, pretty much.
Let me go back to like,
I need to implement something like, what I wanna do is I wanna try cement that kind of, a wind farm thing, like those, the idea is like, wind farm, you can farm half